Let's look at completing the model of the atom. We have been talking about how the nucleus and the protons and the neutrons have been arranged and structured in the atom, but we're still not sure about the electrons. We know what Niels Bohr said, and then Schrödinger with the electron cloud and Heisenberg, but we're still not 100% there yet. We're on the right track. So we're going to complete the model of the atom. Now, we know that Dalton proposed an atomic theory in which atoms were the smallest particles. And then J.J. Thomson discovered the electrons. And then protons and neutrons were discovered. And then Rutherford discovered that atoms are mainly empty space and they contain a nucleus. We're just doing a recap here. And then Bohr suggested electrons revolve around the nucleus. So what do we know? Neutrons and protons are in the nucleus. Negatively charged electrons surround the nucleus somehow. The electrons with the most energy are farthest from the nucleus, and they occupy the outermost energy levels. The periodic table arrangement corresponds to each element's valence electrons. So we can say group 1 has 1 valence electron, group 2, 2 valence electrons, 13, 3, and so on. The period number represents the outermost energy level. So using the periodic table, what do we know about sulfur? So let's look here at the periodic table. We find sulfur. We can find out quite a bit of information. We know it's in group 16. If it's in group 16, that means it has 6 valence electrons. We know it's a nonmetal. We know it's in the 3rd period, which means it has 3 energy levels. We know that it has 16 protons, which means it has 16 electrons. And we can determine the number of of neutrons by saying 32, which is its mass, subtract the number of protons, which is 16. So that would give us 16 neutrons. So the periodic table, as it is now, tells us a wealth of information about sulfur. We might not know the boiling point or the melting point just by looking at it. We might not know what it looks like, but we can determine a lot of information about it still. Now, electromagnetic radiation and energy, we know that light is part of the electromagnetic spectrum. And it can be described as a wave having a range of frequencies and wavelengths. That's why we have different colors and we see different colors. Red, orange, yellow, green, blue, indigo, and violet. They all have different frequencies and wavelengths. Now, the higher the frequency of a wave, the shorter the wavelength, and the greater the energy of radiation. This is just a recap from the image I showed you the previous class. Longer wavelengths and lower frequencies result in lower energy. Electrons can move energy levels by absorbing energy. The energy is released as light when electrons return to their ground state. The emission spectrums for each element has a characteristic set of spectral lines, so we can identify elements and compounds based on They're spectral lines. Now, the big gaps in the spectra correspond to the energy that's released when an electron jumps from one energy level to another. Let's look at the spectral lines again. We have hydrogen and helium. And we see that some lines are more closely spaced together than others. Those closely spaced lines indicate the movement of electrons from levels that are not very different in energy. So let's look at this again. These are closer together. So whenever it moved energy levels, it wasn't as far away as, say, this energy level. The closely spaced lines indicate the movement of electrons from levels that are not very different in energy. These closely related energy levels are known as sublevels, and those are just divisions within a level. If the electrons are distributed over one or more sublevels within the energy level, then these electrons just have slightly different energies. That's why the lines are so close together. There are 4 different sublevels: S, P, D, and F. Now, each energy level consists of these sublevels that are close in energy. Each energy level has a specific number of sublevels. So within a given energy level, the energies of the sublevels from lowest to highest are S, P, D, and F. S has the lowest energy. F has the highest energy. Your lanthanide and actinide elements are in the F sublevel. They are more unstable. They have a lot of energy, a lot of the radioactive elements there. So you can see how much energy it has. So if we look at this periodic table, according to the electronic structure, you have the S block right here, the first 2 columns. The D block is in the middle. The P block is over here. Remember I told you that the transition metals right here and the lanthanide and the actinide series here, they were not predictable with the number of valence electrons. So the lower energies we can predict. The S block here, the P block here, D block, F block. Here is an energy level diagram from first energy level to the 7th energy level. So we have 1s way down here. Then we have 2s, 2p, 3s, 3p, 4s, 3d, and 4p. You could see how closely 4s, 3d, and 4p are together in energy. 5s, 4d, 5p, same deal here. And then in 6, you could see how close together they are in energy. 6s, 4f, 5d, 6p, and then 7s, 5f, 6d, 7p. So you can see how it is. Now I'm going to tell you a little story. I like stories. My grandfather used to tell them all the time. So an electron convention is being held at this hotel. And one electron comes in and they say, "Sir, you can only go to the first floor because we won't fill the higher levels until the previous levels have been filled." And he says, "Okay, that's fine. I'll take the first floor." And he comes up here. Then a second electron comes in, goes to the front desk, says, "I'm here for the convention. He says, great, but we have a different method to this hotel. We have to fill completely each level before we can go to the next. So you have to bunk with the previous guy. The Electron's not happy, but he says, okay. And he pushes his bed to the other side. That didn't come very well because, you know, he wants to try to be as far away from him as possible. So you have one bed up here and then the other bed upside down. So they're on opposite corners. Another Electron comes in and he says, I'm here for my room. The clerk says, wonderful. You get the next room. We only fill according to rooms on that floor, and we can't go up until. So he says, okay. Fourth guy comes, tells the same story. You have to bunk with the person in 2S because we can't go up to 2P floor until 2S is full. That guy sighs, says, okay, pushes his bed to the opposite corner of the room so that they're as far away as possible. And then another person comes in and he says, great, you get the first bed on 2P. Another person comes in and he says, great, you get the second room on 2P. You don't have to fill each room on 2P until all the rooms have somebody in it. Another guy comes in and he's all happy because he gets his own room. Another person now comes in and they said, okay, I'm here for my room. And they said, you're going to have to bunk with somebody else and floor 2P because we can't go up a floor until every room is filled to capacity. We don't open up the floors until every room's filled to capacity. The person kind of rolls his eyes, says, okay, but he does the same thing, pushes it to the other side. So you can see this is how the electrons fill. They can't go anywhere until this is full. So then we get the next floor and so on. It is filled in, the energy levels are filled in an orderly fashion. 1S, then 2S, then 2P, the least amount of energy that it takes. Electrons are kind of lazy like us. They don't want to have to do more energy, expend more energy than they have to. So, okay, if I must share a room, at least I don't have to walk up farther. So that's how electrons are filled. Now, a specific number of electrons go into each sublevel. We know S can hold 2 electrons. P can have 6 electrons. D can have 10. F can have 14. The maximum number of electrons in the first energy level is 2. And that is because, if I show you this slide, there are only 2 elements here in the first row, and they both fall into the S block. So by looking at the periodic table, you can determine which electrons are in which block, which element has whatever block as their valence electrons. So everything here has their valence electrons in the S block. Everything here has their valence electrons in the P block. Everything here has their valence electrons in the D block, and everything here has their valence electrons in the F block. Oh, one more thing looking at this. So S block can hold 2. 1, 2. P block can hold 6. 1, 2, 3, 4, 5, 6. So if you remember where each section is on the periodic table, you'll be able to remember how much each section can hold for electrons. D block can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Lanthanides can hold 1. Get my pen because I don't know if you could see my arrow. And hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So just to give you a little bit more of an idea, a little bit more of a visual you can see there. Okay, let's go back here. Now, orbitals. We have Werner Heisenberg, and he reached the conclusion that it's impossible to measure accurately both the position and the energy of an electron at the same time. This is a Heisenberg uncertainty principle. And the electron cloud model is based on the probability of finding an electron in a certain region of space at a given instant. We also have what's called the Pauli exclusion principle. And it states that no two electrons in an atom can have an identical set of quantum numbers. So whenever I told a little hotel story and one arrow was facing up and one arrow was facing down, they have to do that so that they have different quantum numbers. They have different spins. So one has an up spin, one has a down spin, because all the other quantum numbers would be identical. That can't happen. Now, an orbital is a space in which there's a high probability of finding the electron cloud. And electron clouds are just regions of space located around the nucleus of an atom, and they have different sizes and shapes. The S sublevel we know can hold 2 electrons. It's spherical shaped. The P level can hold 6 electrons, and it's dumbbell shaped. The D sublevel can hold 10 electrons. The F sublevel can hold 14 electrons. And here you can see what these orbitals look like. So this is your F, this is your D, this is your P, and this is your S. S only has one orientation. That's why it has 2. P orbitals have 3 different orientations, and each orientation can hold 2 electrons. D orbitals have 5 different orientations. Each orientation can hold 2, and that is why we have 10 electrons there. The F orbital holds 7 or has 7 different orientations, and it can hold 14, 7 times 2, 14 total electrons. We're going to stop there, and I'll see you next class.